Hello, welcome back. I'm going to continue with the material of chapter 12 that we would have covered in the lab for the Thursday lab. Let me share that document. All right, here we are on page 12 of chapter 12. This is the last section of the chapter where we're talking about reactions of aldehydes and ketones. Aldehydes and ketones can undergo two different reactions, oxidations and reductions. So let's first talk about oxidation. Let's reflect back to when we introduced redox reactions. In biological systems, we can see if a reduction or an oxidation is happening by looking at if there is a gain or loss of oxygen or hydrogen. So in the case of oxidation, we can see either the addition of oxygen or the loss of hydrogen. Let me real quick change my color of my pen. So, how it works in the case of aldehydes is we, of course, for oxidation, you're always going to see that oxidizing agent over the arrow. And what happens here is that the oxidizing agent, it donates an oxygen, and that oxygen does something kind of funny. It inserts itself, it removes the H from the carbon and inserts itself right between the carbon-hydrogen bond within the aldehyde. And this is creating a new functional group. This is called a carboxylic acid. If you recall, carboxylic acids, they are a combination functional group where you have the C double bond O, that's the carbonyl, and then coming off the same carbon is an alcohol group. So that occurs in aldehydes. Interestingly, it cannot occur in ketones. So so here we have a propanone molecule. If we put this in in the environment with an oxidizing agent, since ketones have that carbonyl carbon bonded to two other carbons, that carbon is never bonded to a hydrogen. There's no place for the oxygen to insert itself, and so no reaction occurs. So in these cases, oh, I feel like I forgot to say something. What was it? Yes, okay. So when you have a carbonyl-based functional group in the presence of an oxidizing agent, only the aldehydes will result in a reaction. Ketones will stay put as ketones. Now, earlier in the chapter, and this is what I was going to talk about if I go way back, when we were talking about the oxidation of alcohols. When we look at the oxidation of an alcohol, specifically the oxidation of a primary alcohol, it created an aldehyde. And then that aldehyde, if it is in the presence, which it still is, of an oxidizing agent, then it would form the carboxylic acid that we saw. So if you have an alcohol in the presence of an oxidizing agent, two oxidations will happen. First, it will oxidize to an aldehyde, and then it will oxidize again to a carboxylic acid. If I had this on an exam, I would just expect to see the aldehyde. If you oxidized it all the way to the carboxylic acid, that would also be correct. So I know that your homework will make reference to this double oxidation that happens. Okay, so coming back to where we left off, this oxidation reaction is quite important, actually. And there's two types of tests for aldehydes that make use of this reaction. The first is so they're both tests to give visual confirmation that an aldehyde is present in the solution or substance that you're testing. The first one is more of a generic test for any aldehyde. It's called a Tollens test, and I'm going to do my very best to remember to bring a what we call a Tollens flask. So this is a flask in which a Tollens test has taken place, because something really cool happens. This is a very interesting reaction. So when you put an aldehyde in the presence of an oxidizing agent and you add silver nitrate, the silver nitrate contributes silver ions that have a +1 charge. And what happens is when the oxidizing agent, it will oxidize the aldehyde, just like we learned before, by inserting an O right in there so that our product, everything about the product is the same. We still have this starting point of this this ethyl group, right? Two carbons. One has a carbonyl, and then the O hops in between the C and the H. So that is oxidized because an oxygen is introduced into the molecule. Now, reverse of that, interestingly, these silver ions, they turn into neutral silver atoms. Remember that when we see an element by itself in an equation, we can assume it's neutral. Oh my gosh, review. Okay, so we have silver ions with a +1 charge. They are then reduced into silver atoms with a neutral charge. So remember, when the charge goes down, that means electrons have been added, and that is a reduction. So this is reduced. And that is a redox, right? Our aldehyde is oxidized, the silver ions are reduced. And what's really cool about this is these silver ions, they attach themselves to the container walls. And so I have a flask where the inside of the container of this glass flask has this silver coating because the silver ions deposited themselves onto the glass. This was used to make mirrors when mirrors were, well, mirrors a long time ago were made using this process. Mirror makers, I guess that's a name, would take a flat piece of glass and put a solution on top of that glass that had aldehydes in it, and then they would add an oxidizing agent and silver nitrate. This Tollens reaction would occur. I just realized I have some blanks, so we'll come back and fill them out. And silver ions would deposit on the glass. When they pour off the solution, one side of the glass has silver, the other side is just clear. And so when you look at the clear side, the silver reflects back, creating a mirror. That, of course, is a very expensive mirror because it has silver on the back, but that is an old-fashioned mirror. Now our mirrors are made in a much more cheap manner, but that's what old mirrors, that's how they were made. So let's fill out these blanks. Okay, so our reactants are silver ions coming from silver nitrate and an aldehyde. The products, we're going to get silver metal, which is neutral silver atoms, and a carboxylic acid. Okay. Um, The second test, so we are not actually going to do a Tollens test in lab. I'll bring in my Tollens flask. I hope I will remember. I have one in my office if you want to see it. The second test for an aldehyde actually tests specifically for an aldehyde with an adjacent hydroxyl or alcohol, because remember, hydroxyl is just an OH group. Um, and we will be seeing this test because this is a way to test for carbohydrates, because aldoses have an aldehyde with a carbon with an adjacent alcohol. All aldoses do, because every carbon in an aldose has an alcohol or the first carbon, which has the aldehyde. So this is a way to test for these types of compounds. So we're going to use this to test for carbohydrates in our last lab of the semester. We're going to be separating milk into curds and whey and testing both the curds and the whey for the presence of protein and carbohydrates. So this is called Benedict's test. This is a really cool looking test. It has very vibrant color changes that happen because of changing the charge of copper ions. So copper ions can have multiple charges, and when it has different charges, it will appear different colors. When we add a Benedict's reagent, which contains copper 2 plus ions, these ions are a pretty blue color. When we add that in an oxidizing agent, so I'm just going to add that oxidizing agent. Once again, we see the compound. So here we have, this is 2-hydroxypropanal. You wouldn't have to name this, but we have an aldehyde with a neighboring alcohol. So that's what it tests for. The aldehyde is the reactive part of this molecule. So the oxygen from the oxidizing agent will do what it does and oxidize the aldehyde in the way that we just learned. So let's rewrite everything else in this molecule as the same thing. The only thing that's going to change is the aldehyde. So the aldehyde keeps its carbonyl, C double bond O, but the CH becomes COH, and that's the change. What also is going to happen is similar to what we saw before. So when the aldehyde is oxidized, the metal ions become reduced. The copper ions can reduce in a couple different ways. The indication of a high concentration of these compounds is a red color coming from the presence of this compound right here, Cu2O. This is copper 1 oxide. Oxide ions have a 2 minus charge. So the copper, because there's two of them, they each have a +1 charge. So your copper is going from a 2 plus charge to a 1 plus charge. This is being reduced. And so you go from having this bright blue color to a brick red color. And the color change is very interesting. I think you will enjoy seeing that in real life at the end of the semester. So let's fill in our blanks here. So we have our aldehyde once again with our copper ions and the oxidizing agent. It's going to create our copper oxide. For these reactions, what do I want you to know? They're testing for aldehydes by oxidizing them. And second, I want you to know what color we're looking out for. So in the previous test, the Tollens test, we're looking for silver. In this test, we're looking for a red color, or any color change, really. And then our other product is a carboxylic acid coming from the oxidation of the aldehyde. All right, so that is the oxidation of aldehydes because ketones cannot undergo oxidation. I'll have a third video talking about the reduction of aldehydes and ketones coming up soon. I just want to break this up for you and for me. Thanks.